In Haskell, we often write functions that process lists, and often we like to write them very elegantly as a composition of several fundamental list processing functions. And whenever we do this, then JC actually tries to optimize them in a particular way that often means that the resulting code is actually incredibly efficient, almost as if we hadn't written the function as a composition of different components, but written it as a single loop. And the key to this idea is an optimization that is referred to often as foldr-build fusion, or somewhat more generally as shortcut fusion, or in sort of the old days it was also partially referred to as deforestation. And today in the episode we're going to look at this more closely and to try to understand how it works and how we can kind of rebuild this optimization so that it could also apply to our own implementation of a list library.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes, okay. To start, let's look at a simple example. So this is a really simple pipeline that we see here. Like if we look at this prelude function, which goes from int to int, we create a list of numbers from 1 up to n, then we map the square function over it, and then we sum up all the results. So basically we compute the sum of the first n square numbers. Of course, if you really want to do just that, then there is a closed formula for this, but for the sake of example, this is very similar to the kind of functions that we often end up writing. And so this version here, which is like named prelude, is using just a normal sum, map, and list range function that we get from Haskell, from the standard library. And then I've also re-implemented my own versions of all these functions in this list module. We'll look at this in a moment. And I'm doing exactly the same. The only difference here is that I cannot use the sort of the range notation, but I'm calling my own enum from to function to build this initial list. But otherwise, it's exactly the same kind of pipeline. And then I'm using Criterion, which is a popular benchmarking library for Haskell, in order to compare the performance. So before I actually do that, let's perhaps briefly just verify that these two functions are really, at least on the input that I'm also testing them on, are giving the same results. So prelude 10,000 is giving me this, and own 10,000 is giving me that. So that looks plausible. So now let's just do cabal run, which basically runs the main program, and we are going to see that we get drastically different results, right? So like on different machines, you may get slightly different ones, and actually my machine is now currently also busy with streaming, but it's not it's not close, right? So we have 7 microseconds.
That's embarrassing.
So 7 microseconds for the prelude version, and my nicely written Haskell code gets only to 380 microseconds. So
clearly terrible coder.
Yeah. Okay. So let's see what I did. Right. I try to implement these functions like sort of not in a particularly clever way, but also not in a bad way. Right. So I wrote the sum function as a sort of accumulating loop, right, with an accumulator that I initialize to 0, and then I add in every step. The accumulator is strict, as it should be, and map is written as just a normal directly recursive function, so that it is streaming in principle. And enum from to is a loop, and there are a couple of options here, but basically we have a lower and an upper bound, and so down here we check whether the lower bound is strictly greater than the upper bound. If so, we immediately bail out with the empty list. Otherwise, we call this helper function with a sort of like the current value. And if we enter this helper function, we always produce at least one list element, and then we check whether we've reached the upper bound, and either again we stop or we call go again.
Yeah, so just to be clear, we consider all of these definitions to be perfectly fine. Like there's no
They're
no problem
individually
there.
perfectly fine, and
Yeah.
and I mean they just yeah, I mean there's as I said in the intro, there's a trick that GHC applies, and so basically if we just write our functions like this, we don't get that trick. But basically what I'm going to try to do now is I'm going to explain how the optimization works, and then we're going to try to reproduce it ourselves, so without just going back to the prelude function. So one of the nice things about this foldr-build fusion, I should say at this point, is that it is implemented using rewrite rules. And even though that is tricky, it's admittedly tricky and not something that you probably will end up doing every day, it is something that in principle you can do for your own code as well. So it is not something somehow magically hard-coded into the compiler, and you have no chance to reproduce it for your own code. And so therefore we are going to look at this. Okay, so what's the idea of foldr-build? Foldr-build fusion is named that way because it is based on two functions, foldr and build. So let's actually see if we can get these two functions in. And foldr, probably most of you know, this is an implementation of foldr. So it basically takes two arguments, one which I'm naming cons because it essentially replaces the cons constructor, and one which I'm naming nil, and then it loops over the list, traverses the list, and yeah, it does replace the empty list with nil, and it replaces every occurrence of cons with this cons argument and then calls itself recursively. So basically, the idea of foldr is if you have something like foldr cons nil and you call that on an example list, let's say 1 cons 2 cons 3 cons the empty list, then eventually this will evaluate to something which looks like this: 1 cons 2 cons 3 cons nil. So you get something again which has the same structure as the original list, but every cons constructor is replaced by this function argument called cons, and the empty list is replaced by this function argument called nil. Now let's look at build. Build is having a slightly weird looking type, but really the idea of build is just that we construct a list, right? This, like we want to build a list, by abstracting over the actual types of cons and nil, and perhaps even slightly more generalizing these types somewhat, so that rather than actually directly using the list constructors, we use sort of function arguments that we get from somewhere. And so the idea is that like you can use this build function to build a list such as 1 cons 2 cons 3 cons nil in the following way. So rather than writing what we did before, 1 cons 2 cons 3 cons nil, we would write build. And then to build, we pass an argument, which I call the builder. And the builder is a function which takes a cons and a nil. And then we just construct 1 cons 2 cons 3 cons nil. And I'll be explicit about the parentization here. So this is still supposed to be right nested, right? Mm-hmm. And if we now run build on this, then like the argument cons is going to be instantiated to cons again, and the argument nil is instantiated to nil, the empty list again, and we get back the list 1, 1, 2, 3. Right? Why is this function build interesting in connection with foldr? Well, because if we now assume that this list here had been written using this build style, right? So if I get rid of this, sorry, and then paste this in, let's see, like this, right? Then it kind of cancels each other out, right? So foldr and build more or less cancel each other out, and we can immediately return this with this version of cons and nil, right? So the idea is that we never, if we have foldr and build sort of chain together like this, we never actually have to instantiate this cons and this nil with the actual list constructors. We can immediately take the arguments of the foldr function for this. And this gives rise to what is called the foldr-build optimization rule. So in general, this is called, it looks like this. If you have foldr cons nil, and then you have build applied to a builder, and a builder is such a function that constructs a list but is abstracted over cons and nil, then we can basically say this is the same as calling the builder, right, this function here, but now this function expects cons and nil as arguments, but we just pick the two arguments of foldr.
So just to be very explicit, rather than first building the list and then consuming it again by folding it, we avoid this build and then deconstruct again, and we fuse them together to get just the final result immediately.
Right. Yeah. So this is the whole idea in principle, right? That you can, like, if you have something that constructs a list and you can write it using build, and you have something that consumes a list and you can write it using foldr, then you can in principle try to apply this rewriting in order to get rid of the intermediate list. And if you have a pipeline where this occurs multiple times, you can even try to do this multiple times and get rid of multiple intermediate lists in principle, right? So this idea goes back to a paper by let me see, by Andy Gill, John Launchbury, and Simon Peaton-Jones, which is called A Shortcut to Deforestation. And I'm not sure whether the year number is listed here. It's relatively old. It goes back to the early days of Haskell. It's like 1993, right? So so this is really...
Haskell was a few years old.
Yeah, I mean, a lot has been written about shortcut fusion and all sorts of other forms of fusion in the meantime, right? So this is there are many other options as well than just this foldr-build fusion, which we are looking at here, and they all have their different trade-offs. But foldr-build fusion in the style described in this paper is used to this day in the list library of GHC. So that's what we're going to look at today. So how do we get the compiler to apply this? Obviously, this is sort of an observation that we have taken, but it involves like a recursive function foldr, and like if you really want to make it clear that this is really correct, you have to be a little bit less hand-wavy than we have been. So you cannot really expect the compiler to magically figure out that this equation holds and apply it completely on its own, but we can use a rewrite rule in order to tell it so. And this is what we can do by means of the general GHC rewrite rule mechanism, which is done by means of a pragma, which is called rules. And in a rules pragma, you can define one or several rules. And you have to give a rule a name. So let's call this one foldr-build fusion. So the name is just a string. And then as a first approximation, you just define the equation. That's not the full syntax, but you can start with this. And now you can actually like follow the error messages. So like HLS, like Haskell Language Server, is actually helpfully type checking this pragma for me and is giving me error messages. So you're supposed to quantify explicitly over all the things that are parameters to the rule. Like foldr and build are functions that we are using, but cons and nil and builder are parameters, and whatever values we find we want to use. So we just use for all cons nil builder here. And then we get another error about builder, and that is a little bit of a tricky to read error. And this is due to this rank 2 type signature that build has, like that the argument of build is itself polymorphic in the result type. And like in order to make GHC accept this, we simply have to annotate the type of this explicitly. So we have to basically repeat the type of this argument, a to r to r to r to r. And then because this gets very long, let me just try to split the whole rule onto 2 lines. And now this is in principle accepted, but I still get warnings. And these warnings, they are actually good. I mean, in the old days, GHC did not produce them, but it is a very helpful warning, actually. Namely, it says that these rules are now there, but they may never fire. I mean, and they're actually very likely to never fire, to never be applied. And why is this? Because GHC is already very keen to optimize our code in all sorts of ways. And for many functions, it will actually apply inlining. Right? It will try to reduce these functions. In particular, build is a small non-recursive function, so GHC will be extremely keen to just inline build. And the moment GHC inlines build as a function does no longer appear in the code. And if GHC tries to look for the left-hand side of this rule, it will no longer match. And even foldr being a recursive function can be inlined partially by means of the worker-wrapper transformation, which we are not talking about today. But so in general, you have to be very, very careful that if you write rules, you are sort of slowing down GHC's inlining to some extent, right? And now,
well, you want to slow it down. That's kind of the point, right? You want.
Yeah, we want to slow it down, right? We want to make sure that potentially build is still being inlined, in particular if it cannot be fused, but not too early, right? And so that is something we can say by using yet another pragma, which is called inline, and then give a phase annotation, and then just put the function name there. And okay, so these phase annotations, we don't have time today to really talk about them in detail. They are described in the GHC users guide. Roughly speaking, the simplifier, so that the optimizer is running through different phases. It's starting with a high phase number. So I think it's actually, depending on how you look at it, there are 3 or 4 phases. So, for example, at some point there is a phase with the number 2, and then there is a phase with the number 1, and in the end there is a phase with the number 0. And what we're saying with this inline bracket 1 is that we do not want to inline before phase 1 is being reached. So like in particular during phase 2, we do not want to inline build, so that, for example, this foldr-build fusion rule has a chance to fire.
Right, and so phase 2 comes before phase 1, just to be clear.
Yes.
First
so
apply the rules,
they're counting down. They're counting down.
Right.
Yeah.
Right.
And similarly for foldr, we can do something similar, but I'm going to actually write no inline 1 here for foldr, which has a subtly different meaning. So no inline 1 again means do not inline before phase 1, but afterwards we don't care. So basically, like from phase 1 on, we don't care. Like if GHC wants to do worker wrapper or something like that, it can. We are not preventing it to, but we are not saying, like with build, be very keen to inline later on.
We could have done the same thing with build too, I suppose.
We could have done the same thing with build too. Yeah. I mean, that I think would be very safe to put no inline.
Because GHC would still make the same decision after.
Yeah, I guess so. So this is it. Like the important thing is that basically before phase 1 has been reached, we are preventing the inlining of both these functions, and therefore we are making it possible that the rule actually fires. Okay. Mm-hmm. So now, of course, we are only halfway there. Now we have implemented a foldr-build fusion, but we have to actually write our other list processing functions in terms of foldr and build, and we have to do this for the 3 of them. And I'm going to just write different versions of these 3, which I'm going to call slightly differently, and then I'm going to use rewrite rules again in order to rewrite the original version to the modified version. There are other ways in which we could be doing this, like we could be using inlining there or something like this, or we could replace the original function definition completely. There are all sorts of trade-offs there, which we don't have time to go into. In particular, if you have other use cases or you have other kinds of rules you want to apply for the same kinds of functions or this sort of stuff. So, but we're going to just see it as an exercise now to transform these three functions. Let's actually start with what is probably the most tricky one. So some we want to write as a fold-r, even though it looks to people who know like folds more like a fold-l prime. But fortunately, all these accumulator style functions can actually be written using fold-r. So in particular, fold-l prime itself can be implemented as a fold-r. And the trick is as follows. You basically change the result type to be a function, and we can do that here by flipping the arguments of Go. So let's introduce an argument list here explicitly, and then let's flip the two arguments of Go and put the list first and the accumulator second. So as an intermediate step, let's do it like this, right? Accumulator, and then the recursive call as well. So this one type checks again. And now we move the accumulator over to the right-hand side as a lambda. Right. And now this actually does have the shape of a fold-r, because like in the empty case we replace with the identity function essentially, and in the cons case we just replace with a recursive call on the tail of the list, and that's so we can transcribe this to a fold-r almost mechanically. So we have our list. And in the end, we apply to 0. That is coming from this here. So basically, the fold-r is sort of playing the role of Go now. And in the empty case, we use ACK to ACK. And in this case, we use ACK to. And so Go XS is our we get our X, we get our recursive call, and we then produce a function that takes the accumulator to the recursive call. Go XS is the recursive call applied to ACK plus X. Okay. And okay, so
the first two arguments there are the normal arguments you get from fold-r all the time, and then this ACK is the sort of the third argument, which you get because we are producing a function as the result of a fold-r.
Yeah, exactly. Yeah, we can simplify slightly, of course. Now that we have done this and it does work, we can remove this nested lambda. And also here, the identity function is strict anyway, so we don't really need the bang. We can perhaps slightly simplify and simply put the identity function there. But it's a matter of taste. Okay, and this one we actually do want to inline, right? Because yeah, I mean, this is just a wrapper around a fold-r call, and yeah, I mean, so we basically want to expose the fold-r call for foldr-build fusion application as much as possible. Now, map is simpler. I think, as I said, sum is probably the most tricky of the three. The only tricky thing about map is that it is consuming and producing a list, and then you just basically have to know that sort of the best way to do this is just to, like, after we've taken the f and the list argument, we're supposed to produce another list, and we're going to do that using build. So we're calling build, which then takes a builder, which gets this cons and nil argument. And then at this point, we're going to consume the input list using fold-r. And so fold-r again takes two arguments and then consumes the list. And if we get the empty list, we build an empty list again using nil. And if we get a non-empty list, then we get an x and a recursive call, and we produce a cons of f applied to x and r. Right? Okay. And enum from 2 is actually very easy to change, even though it is like sort of a lengthy function, but it is just a builder or a build essentially. So so the only thing we have to do is to call build, and we get cons and nil. And then we copy all this code here. And now we just replace all the occurrences of the empty list with nil. And the one occurrence of cons with cons. And that's it. Okay, now I need yet more pragmas. I want to inline mapfb. And I want to inline enum from to fb. And I need some way to establish the relationship between sum and sumfb, and between map and mapfb. And again, I can just use more rewrite rules if I want for this. Again, like, I mean, I could do this in some other way, but this is one simple way. So let's actually try this. So let's also do the indentation so that they all match. So these are just 3 rewrite rules that are saying, okay, if I see sum, I want to rewrite it to sumfb. If I see map, I want to rewrite it to mapfb. If I see enum from 2, I want to rewrite it to enum from 2fb. And now the same thing again as before, that sum must not be inlined too early. So let's put no inline 1 on sum again, so that like in the beginning of the process, we have a chance to have rules fire. No inline of 1 on map, and no inline 1 on enum from 2.
I don't know if you want to go into this at this point, but I'm just curious now that I'm. Could we either use these laws? Could we just say sum equals sumfb?
Yes, I think so. I think that should be fine. Yeah.
Okay.
I mean, let's just try that out. I mean, first of all, let's just try to run this again and see what we have now. And now we actually, like, it's actually faster.
We beat GHC at its own game.
So the reason for that is that like GHC does something slightly different with enum from 2 than what we are doing. It applies a slightly different rule there, and there may be good reasons for that in other contexts. I'm not going to say that, like, I mean, we're doing better, and there may be good reasons, but we are the important thing is we are in the same ballpark, right? So we are like, even if we were slightly slower, I mean, the point is we are no longer at, I don't know, 300 microseconds, but we're sort of more or less in range of the whole thing. An interesting thing that we can also do is we can like tell GHC to tell us during compilation which rules are being applied, right? And if we do this again now, this is actually surprising. Oh no, this is. Wait a moment. No, now I'm confused. Map fby. Oh, I should not have. Should not have done this.
We don't need to debug this on there right now. It's.
Yeah. Oh, I'm putting it on the wrong module. That's why. Yeah, I'm doing the pipeline construction is in main, right? And so this is where I want.
Right. When we we are compiling main, that's when we want these rules.
That's when we want these rules to
Right.
Okay, yeah. So this is looking much more than what I want. So if I break here, we can see that foldr-build fusion is being fired twice, right? Because we have a composition of 3 functions, so we have 2 opportunities for fusing them together. And similarly, we actually see that the built-in rule for the prelude foldr-build fusion, which is called fold/build, is also fired twice.
Because we still have the other example.
Yeah, because we have the other example in there.
Yeah.
So so that's interesting. I guess we are more or less at the end. Do we have questions?
No.
Okay. So perhaps, I mean, one thing that I could still show briefly is sort of like what kind of code is like actually being produced. I mean, we can of course look at the core output, but I'm going to show this briefly in the surface language, perhaps. So if we look at the example again, which is this one, right? And we simply take our definitions of these 3 component functions. So this was the definition of enum from 2, right? So that is the innermost thing. I'm calling the result of this R0. And then we have our definition of map, which is this fold-build fusion, which we call on the result of R0. And then we call sum, which was defined like this on R1, like with this 0 initial argument, and then in the end we return 0. And so then we can fuse this twice, right? So the first step, if we for example fuse R0 into R1, so basically we take this map call and this enum from 2 call, and we glimpse at it, there is not very much that is really happening, because we have a build call here, we are replacing this with another build call, and nil is being replaced by nil, and the only thing that cons is being doing is that cons takes like 2 arguments and is replacing its left argument with x times x, and cons is applied here, and the left argument of cons is I. So what happens if we fuse these 2 functions is that we get like almost the same enum from 2, only that in this place we have I times I rather than a plain I.
So now we're directly building the list of squares.
Yeah, now we're directly
in
building
one
the
step.
list of, yeah. And then if we fuse the other 2, this is like ever so slightly trickier, right? Because there is this extra argument. That's why I've been doing this slightly more slowly. So I'm basically just saying, okay, so this is what cons becomes in like the build is being stripped, right? And like this application of cons becomes that, and this application of nil and this application of nil becomes the identity function. I'm doing this just via a let in this step. So here cons is like this argument, and nil is the identity function, and this is the same enum from 2 build where we are already building the list of squares. And then if we're doing a little bit of substitution and simplification, right, then we get a loop that looks just like this, right? And that is, yeah, I mean, that is what we could have written by hand as well, but it looks much less like compositional and nice, right? But I mean, it is relatively easy to see that this is also doing the right thing. Like we are, we're initializing the loop with sort of our counter and with the accumulated sum. And then every step we check whether we have reached the upper bound, and if we have reached the upper bound, then we are still adding the sort of the current square, and otherwise we are calling the loop again with an incremented counter and also an incremented accumulator. And that's
right. So the paper that says like we want to have our cake and eat it too, right? That's kind of what's happening here. Like we have this nice, elegant composition of functions, but yet in the end, we end up with this perfect loop that would compile down to a single like jump in machine code. You know, this is as good as it gets.
Yeah.
So
yeah,
fairness.
I think this is basically it. I mean, I think for fairness, we should say like fusion done via rewrite rules is a little bit fragile, right? So there are ways to, not just by writing our own list functions, which are not like written in the right style, but also by sort of spreading things across different modules. And because there is this trickery with the phases and the inlinings, the unfoldings have to be available, but not available too early, and so on and so forth. There are heuristics being applied. So it's possible that sometimes it doesn't work. But as an opportunistic optimization, it's great, right? Because it really makes a massive difference. So yeah, I mean, I'm a little bit torn sometimes, because it's nice to have reliable optimizations, and like rule-based optimizations are not extremely reliable. They're still okay, but they're not extremely reliable. They're a little bit fragile. But overall, I think it's a cool thing, and it is cool that this mechanism and principle is extensible, and you can do your own thing, and you can look at the base library in GHC, and you see that the fold-build rule is somewhere in there, and it actually looks more or less like the one that we have written, just with different variable names. And you can see that there are lots of other rules as well to try to make it like even better and cleverer, right? And to cover other cases as well. Okay. I guess.
So thanks everyone.
Yeah.
Thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And feel free to leave any comments below. We'll leave the chat open for a couple of more minutes if people want to ask any more questions. And I think we're not going to be back in 2 weeks as we would normally, but probably in 3 weeks. But we'll post on various social media to announce it.
Okay.